Here we'll consider another problem involving friction. Here we have a 20 kilogram mass sitting on the table, and the coefficient of friction between that mass and the surface of the table is 0.41, and that mass is connected by a string that runs across a perfect little pulley and then down to the 6 kilogram mass. We want this to be a kinetic friction problem. So if the system is not already in motion, give the 20 kilogram mass a little push to the right to get things moving. Now, to look at this, let's kind of clean the slate a little bit and put in some of the significant information. For talking purposes, might be convenient to refer to the masses as 1 and 2. So here we have mass 1, and there's mass 2. Mass 1 from the previous slide was 6 kilograms, but that's a little bit in the way, so here it's written off to the side. And the mass of object 2 is 20 kilograms. We need to look at what forces are involved, and, well, that will result in accelerations. If we look at object 1, let's assume, we don't really know for sure, but let's assume that it's accelerating downwards, in which case the acceleration, the a1y component, would be a positive number. But it's actually possible, we just don't know at this point, that the acceleration is the other direction, and that could end up being a negative number. Nevertheless, we're going to look at the accelerations of the masses. And there's the a2x, and then the forces that are involved with each mass. Gravity is trying to pull mass 1 downward, so that weight, let's say, is W sub 1. There's also a tension force being delivered to mass 1 that's coming through the string, basically because mass 2 on the table has inertia and it's resisting the motion as gravity is trying to pull object 1 downwards. The tension force gets translated through the string, so there's also a tension applied to mass 2. As mass 2 is moving, if it's moving to the right, there's going to be a friction force to the left. We'll call that F sub 2. Even though F sub 1 doesn't really exist in this problem, I think the subscript is still helpful to keep everything straight. The friction force is going to depend on the normal force. So with mass 2, gravity is trying to pull it down, but the surface of the table is opposing that and applying a normal force, kind of pushing upwards on object 2. The normal force and the gravitational force for object 2 will cancel out, which is going to tell us that the normal force just equals the weight of object 2. The weight of object 1, of course, is going to come from the mass times the acceleration due to gravity. And we'll go ahead and plug in some numbers. The mass of object 1 is 6 kilograms. Acceleration due to gravity is our old friend, 9.8. That gives a downward force of about 58.8 newtons applied to object 1. I've also said that the normal force applied to object 2, the force the surface is applying to the object, just has to balance out the weight of the object. So that normal force is going to be the weight of object 2. We could go ahead and plug in numbers, but I'm going to hang on to that for just a second. It is going to come from the mass times gravity. That's what we'll hang on to for a second. The friction force is proportional to the normal force, and there will be the coefficient of kinetic friction. But now the normal force is the same as the mass times gravity. So I'm going to plug it in at this point instead of putting numbers in too early and having to use the calculator more times than necessary. But still, here we'll plug in, so the coefficient, 0.41 times the mass of object 2, 20 kilograms, times acceleration due to gravity, 9.8. That all works out to about 80.36 newtons. So those are going to be the forces that are involved here, but there are a few more things to comment on. Although it doesn't show up in this problem, if we needed the velocities of the masses, it's worth noting that the velocity of object 1, as it's going down, is going to be the same as the velocity of object 2 as it's going across. That's assuming that we pick the coordinate systems appropriately. I haven't really put that in here quite yet. It's going to show up in a minute. But it's also a little bit awkward to have something with the y component equaling something with the x component. So if I were really working this problem and needed the velocities, I might just call it v. But I still have to bear in mind that that velocity is indeed a component and can be a positive number or a negative number or zero itself. The velocities match up, but that also means that the accelerations match up, and we will need those in this problem. But again, it's a little bit awkward trying to match the A1 y component, the A2 x component. So I'm just going to call both of those A. But again, that is a component, could be positive or negative. So if we get a negative result, shouldn't be too surprised by it, at least mathematically. And it's also still true, well, if the pulley is perfect, if the string does not have any mass, if the string does not stretch during the dynamics going on in the problem, then the two forces, the tension force on object 1, the tension force on object 2, are going to equal each other. It's kind of Newton's third law in following along the string. Since they're equal to each other, don't really need subscripts there, so we'll just call them T. Now I'm going to kind of clean up the picture once again and put in the values that we know at this point. So that's kind of neat, thanks to PowerPoint. So now the accelerations are just called A. The forces, the weight, the 58.8 newtons. The friction force, 80.36 newtons. The tension forces, now just referred to as T, have been put in. And at this point, can't really get by without it any longer. Need to specify the positive directions. And it's going to turn out in this problem it's a little bit easier to think of down as the positive direction and to the right as the positive direction, so that those are both sort of in the same sense. As object 1 is going down, object 2 is going to the right, and that kind of matches things up in a pretty nice way. Now, if we use net force equals mass times acceleration on each object, we'll get some equations that we can deal with. If we look at object 1, the net force on object 1, its motion in the y direction is going to be the mass of object 1 times its acceleration. But using the values now in the diagram, we have the weight of object 1 minus the tension of object 1. That's really an addition of forces, but the tension is pointing in the negative direction. So that ends up being a negative of the tension. But putting the values in now that we have 58.8 minus the tension, it's going to equal the mass, 6 kilograms, times that acceleration, just calling it the uppercase A now. But that's one equation. It has two unknowns in it. We need a second equation. The net force on object 2 is going to equal that mass times its acceleration. The forces acting on it are the tension and the friction forces. And plugging the values that we know at this point, the tension, we're just calling it T, the friction force, 80.36. It's going to equal the mass, 20 kilograms, times the acceleration, uppercase A. And that gives us two equations, two unknowns. Relatively simple, though. It can be done by substitution. It can be done by linear combinations, adding the equations together. Whatever the case, let's kind of get fresh here. And we have two equations, two unknowns, just copying them over on a fresh slide. And I'm afraid I'm not going to work through the math here, but a great way to do this problem is to take the two equations and add them together. Because then for the left-hand sides, the minus t and the t will cancel out. On the right-hand side, you have the 6a plus the 20a would give 26a. The results will just follow very quickly. Nevertheless, here, I'm not going to write out the math. I'll just point out the solution is going to be the acceleration is negative 0.829 meters per second squared, and the tension is 63.78 newtons. That negative acceleration is telling us that if we look at the first object, the one hanging over the side of the table. While we know that it's moving downwards, that negative acceleration tells us that it's slowing down. The friction force is great enough in this system that it's slowing the object down. That's where the negative shows up.